So we are going to finish problem 16 like I promised. And we're going to need to get this iPad going. So problem 16. There we go. So we're going to integrate over the real number line because this is from negative infinity to positive infinity. And that's over the real number line. Okay. So we're going to split this interval and go from negative infinity to 0, x e to the minus x squared dx, plus integrating from 0 to infinity x e to the minus x squared dx. So you have two integrals here. And like we described earlier, maybe you can call this integral A, integral B. And in order to have convergence, we need both of these to be finite. So we're going to integrate 2, possibly. So we'll start with the first one in gray. So A is going to be the integral from negative infinity to 0, x, yeah, that's x, e to the minus x squared dx. That's defined to be, because this is an improper integral, the limit as t goes to negative infinity, we integrate from t to 0, x e to the minus x squared dx. So let's integrate by u sub. So this is going to be a u substitution, where u is minus x squared, which means du is minus 2x dx. Dx is du over negative 2x. So we're going to integrate by u sub. And the x cancels, so we get this equal to, we'll put it next to this. This becomes the integral of e to the u du over the negative 2, but we're going to pull out that constant. So we see this integration by u sub a lot. Now, remember, this is x goes to, or x equals t as a lower limit, and this is x equals 0, so we got to go plug back that u here, because u is minus x squared. Minus 1/2 e to the minus x squared evaluated from x is t to x is 0. So, okay, we integrated this. We need f of 0 minus f of t, which is negative 1/2 e to the minus 0 squared minus a minus 1/2 e to the minus t squared. Which means this first portion is going to be really e to the 0, which is 1. So this is 1. And the minus a minus makes that a positive 1/2 e to the minus t squared. Really minus 1/2 now. And this is what we called earlier today your integral with respect to t, I of t, which is really the a we also, well, it's not the answer, but we now got to take the limit as t goes to negative infinity, 1/2 e to the minus t squared minus 1/2. Because we got to apply, again, this limit portion here. Okay, and this was the I of t we just got. It's really I1 of t. All right, we talked about this earlier. So that limit, this is what we're applying now. Limit as t goes to negative infinity. By properties of limits, we get 1/2 limit t goes to negative infinity e to the minus t squared minus 1/2, because the limit of a difference is difference of a limit. Limit of a constant is the constant. We pull out the constant of 1/2. Now we have to figure out, where does this go? Okay. So as t goes to minus infinity, we know t squared goes to infinity, which also means minus t squared goes to minus infinity. So e to the minus t squared, well, we got to know about that exponential function. And if you recall your exponential curve, as you go to minus infinity, this goes to 0. So, okay, sure enough, we end up here with this integral converging. It equals negative 1/2 here. Okay. And so that's the first a. A goes to negative 1/2. So this is what we're talking about here. This equals negative 1/2. We have convergence for this first improper integral. This one goes to negative 1/2 is what we're saying. And so what you can see here now is they're saying that this area is negative 1/2. And that makes a lot of sense because the curve is below the x-axis. And remember what we mentioned earlier, that those approximating rectangles that we drew here, okay, that's below. So it's a negative area there. So it makes some sense that that should be negative 1/2. All right. So we have convergence. So there's convergence for this first improper integral. And now we have to determine the second improper interval we call b, and that goes from 0 to positive infinity. If we get convergence here, then this integral converges. So we need convergence for both. Okay. We're going to need more paper. Now, b is the integral from 0 to infinity x e to the minus x squared dx. That's the same, well, I shouldn't say it's the same integral. It's a different improper integral. This is our t again. So the limit as t goes to infinity, we integrate from 0 to t x e to the minus x squared dx. Now, what I started to say essentially is here we would do u sub. It's the same function we're integrating, but different limits. So by u sub, we already know what that was because we've integrated this. And by u sub back here, this is what we end up with. Negative 1/2 e to the minus x squared. But the limits are different. Okay, it's a different improper integral. Negative 1/2 e to the minus x squared. So negative 1/2 e to the minus x squared evaluated from 0 to t. So we need f of t minus f of 0 here. And I'll use blue. F of t minus f of 0. Negative 1/2 e to the minus, now that will be t squared, minus the negative 1/2 e to the minus 0 squared. Where you really have e to the 0, which will be 1. So this is negative 1/2 e to the minus t squared plus 1/2. And like I've been doing, I like to start with a positive term, so I switch these terms. Addition is commutative. So now, again, this is the I2 of t. We have to take the limit of this. There we go. And this is now the limit as t goes to infinity. So t is going to infinity here now. So let's apply the limit. Limit as t goes to infinity. 1/2 minus 1/2 e to the minus t squared. By properties of limits, we get 1/2 minus 1/2 limit t to the infinity e to the minus t squared. And now we need to find where this limit goes to. So let's go through the logic. As t gets big, t squared gets big, and minus t squared goes to negative infinity. So then e to the minus t squared, well, this will also go to 0 for the same reason. Okay, so let's kind of take a look at that again to double check and make sure we have an exponential function and the power is going to negative infinity, which means we're going to 0. So remember, this is where t is here. So this is 0, which means this limit is positive 1/2 now. Okay, because this is the constant that's there. That's the 1/2 we're talking about. So this equals 1/2. So we have this integral b, this improper integral, equal to 1/2. And if we go back to that picture now, that makes a lot of sense because this is a positive 1/2. Now, to make a long story short here, okay, if we can draw this correctly, negative 1/2 plus positive 1/2 equals 0. So 0 is a nice finite number. This is finite. So we have convergence here, and this is what we're looking for. So we have done this last question. The area under this curve over the whole real number line is actually 0. And you can actually see this by the picture because, again, the approximating rectangle for the interval from 0 to positive infinity is a positive answer, but it's the same because of symmetry. It's opposite in sign, positive 1/2 versus a negative 1/2. So when you add the two, right in here, we're adding them, the sum is actually 0. So there we go. So I hope you guys enjoyed the demonstration. I'll send this to you, and you have a nice evening.